Okay, so I'm sorry I wasn't here Monday and Tuesday. My dean said I had to be in Austin yesterday for a meeting. So I just got off the airplane. And so I apologize if I repeat some things that have already been said in the previous 2 days. What I'm going to talk about is connected to the theme of this conference, which is really trying to do predictive theory and computational modeling of the properties of two-dimensional materials. And I'm going to talk about Moiré superlattices formed from two-dimensional materials. And even though, as I'll maybe mention at the very end, some of the other systems might ultimately turn out to be more interesting or just as interesting, I'm going to talk all about magic angle twisted bilayer graphene. And so here's the theme. Whoops. This worked a moment ago. Maybe I'm too far away. I'll do it from this side. Yeah. Okay. Okay, so theme of the first part of my talk is that it's challenging to do predictive modeling of the interesting electronic properties of magic angle twisted bilayer graphene. And I'm going to talk about some of the reasons why it's hard, okay? I'll come back to this phase diagram later, but for the moment, I just want to say, draw attention to the two axes of this phase diagram. One is an interaction strength parameter written as 1 over a dielectric constant. The biggest number here corresponds to Coulomb interactions screened by surrounding the material with hexagonal boron nitride dielectric. But the interactions, as we well know from experiments we'll hear about later today, and you may have already heard about earlier, that interactions are weakened if the electrical gates that are always used to manipulate these 2D materials are nearby. So the interaction strength goes down, and there may be other reasons why if your theory leaves out certain processes that can be boiled into a dielectric constant, you might do a theory with other dielectric constants. And the other parameter in this phase diagram is twist angle of 2 layers. And what this mainly shows that the gray region of this phase diagram basically means nothing interesting is happening. And the interesting physics then in the blue region occurs when the twist angle approaches 1.1 degrees. And as you all know, what's happening there is that you have a group of electronic states that are very close in energy, so all of the physics is dominated by interactions. So we're interested then in magic angle twisted bilayer graphene, 1.1 degrees. That's a very small twist angle, and that means the Moiré pattern contains many, many atoms. So there are probably there's some motivation sometimes for trying to understand the properties of twisted bilayers by really doing it fully microscopically. But usually that's kind of awkward or not very revealing because there are so many atoms per period of the Moiré. 10,000 or so typically, and it's not even true in a generic sample, of course, or for generic twist angle that you actually have a crystal. So we want to do a theory in which we only keep track of the Moiré physics and not of the microscopic atomic positions. And so I'll describe that approach, what I think of as a continuum approach, and see what some of the problems we run into within that approach. Okay? The fully microscopic approach, of course, is well motivated for looking at some questions. So these Moiré superlattices formed by small angle twists in the context of condensed matter physics, they're interesting because they simulate crystals. It turns out, as I'll emphasize, the systems are very accurately described by a periodic Hamiltonian. And we can use all the simplifications that we use in solid-state physics of crystals. And there have been many attempts over the years to make long-period artificial crystals out of that simulate condensed matter, and using, for example, lithographic techniques that our engineering friends are so good at. But you can't do it well enough. Somehow this seems to work better than anything else. And of course, the motivation for making very long period superlattices is that the size of the unit cell of these artificial crystals is about 10 to the minus 12 square centimeters. So a band in a crystal has will hold 1 electron per each unit cell. So this electron density that corresponds to filling the bands of these artificial crystals is around 10 to the 12 electrons per square centimeter, and that's comfortably in the range where you can add and remove those electrons that fill those bands with electrical gates. Okay, that's why the gates are always there, because we want to do that. It's the main motivation for this. And that's something we can't do with real crystals. We cannot change the number of electrons per atom, and that is a really powerful thing in understanding probing experimentally the properties of a system. Okay. So the idea, as you all know, of this continuum approach is that the Hamiltonian is replaced by becomes a position-dependent Hamiltonian, and the position dependence is controlled by the variable that varies locally in the twisted systems, which is the local displacement of one layer relative to the other, the local stacking, if you like. And so if you rotate one layer relative to another, then let's say you rotate the top layer, then the distance an atom in the top layer moves is proportional to the distance from the axis of rotation. But what's important for the local properties is the displacement modulo the lattice constant of the two individual crystals. And it turns out, or you can easily see, that quantity is periodic, and that's basically the periodicity of the Moiré pattern. Now, a Hamiltonian of a crystal is usually formulated in what's called K dot P language, but the Hamiltonian depends on momentum, just like the energy of a particle in free space depends on momentum. And so here this Hamiltonian depends on momentum, and as I move through the Moiré pattern and vary d, it depends on position too. And so we all know in quantum mechanics we can't precisely define position and momentum, and so in this type of description works when all of the states you're interested in are close to a particular momentum of the microscopic crystal. And then you can just evaluate that Hamiltonian at the momentum that you're interested in. And so this actually requires that the stacking very slowly in space, which is that the twist angle is small. Okay? So you can only do this in small twist angle, and it's not true in a usual metal that you're only interested in states that have very nearly the same momentum. Instead, you're interested in states with many momentum. So you can only do this in semiconductors and semi-metals. Okay. So I'm coming to why it's challenging to make predictions using this approach. But what I'm showing you now is an illustration by a paper I wrote with Rafi Bistritzer. And what it's a plot of basically is how the tunneling amplitude in bilayer graphene. Bilayer graphene has, of course, two different sublattices of the crystal. And so it's the tunneling amplitude at the momentum we're interested in from one sublattice of one material to, this is actually, I think, forget which one this is, but from some particular sublattice of one of the two layers to some particular sublattice of the other two layers, and how it varies. It's a complex number here, written as an arrow, with the direction being the phase of the complex number, and the length of the arrow being the magnitude of the complex number. And so you see it has some spatial pattern, and that is sort of at the microscopic level. That's the way in which the Moiré pattern influences electronic properties. Now, I want to mention one property of the important part of the tunneling for bilayer graphene, which is tunneling, sublattice-dependent tunneling from one layer to the other. And normally, I said that the Moiré pattern is periodic when you translate by a one lattice constant of the Moiré pattern, then the local stacking is the same. But if I look at the block Hamiltonian, the momentum-dependent block Hamiltonian, that Hamiltonian is not invariant under a translation by L here is supposed to be a lattice vector of the Moiré pattern. And the Hamiltonian is not invariant. And the reason it's not invariant is because we're interested in the hopping between block states that are at this momentum, big K, which I'll emphasize again later is at the corner of the Moiré-Bruin zone. And so when I shift one layer by a lattice vector, then maybe I should have written this slightly differently. But when I shift one layer by a lattice vector, and I'm using, let's say, some tight binding model with well-defined atomic wave function, then the wave function shifts by a phase factor. So this Hamiltonian actually doesn't have the periodicity of the Moiré pattern. Instead, it has this extra phase factor. And so when we analyze properties of crystals, we often use the property that periodic functions, when you expand them in Fourier space, the only non-zero components are reciprocal lattice vectors of the crystal, which is what you see in electron diffraction pattern. When a function that has this property, it turns out there are a different set of wave vectors that appear in its Fourier expansion, but you can easily determine what they are. And here is something similar calculated in a different way. This is a particular sublattice-dependent interlayer tunneling term. It's calculated from a Wannier function, tight binding model derived, and tight binding model. So it's calculated from ab initio density functional theory calculations, and this is actually its dependence on position in real space. But if you Fourier transform it, it turns out that there are 3 different wave vectors that have Fourier coefficients that are much, much bigger than the others. Okay, and this is, this is the same thing that, for example, in Rafi Bistritzer's paper was derived from a tight binding model, but it has nothing to do with the tight binding model, only has to do with this translational symmetry property, and with the fact that in these van der Waals crystals, you have layers that are far apart. And when you have things that are far apart, it's hard to see small length scale spatial structure. So that means expansions in wave vector space converge rapidly. Okay, so that's the idea. This is the point made in this figure in the paper with Rafi Bistritzer, and the argument is that you don't need to have a microscopic theory. It's only these Fourier coefficients of at the 3 smallest wave vectors, which you need to keep account of in your theory, and they're related to each other in a simple way by symmetry. So we thought actually there's only one number that controls the electronic structure, and so whenever you have a property that depends on one number, better to get it phenomenologically than to calculate it. Turns out actually there are 2 numbers, as I'll mention in a moment. Okay. So this is a calculation from Rafi's paper. It is 2 layers of graphene, 2 layers of graphene coupled by sublattice interlayer hopping, which has the smooth spatial pattern I've been talking about. And it turns out that model is basically defined by total electronic structure, depends only on twist angle, and the layers get more strongly coupled as you go to small twist angles. So at somewhat larger twist angles, then you can see here basically 2 Dirac cones displaced in momentum space that are crossing each other. And then you go to the magic angle where these flat bands appear, and we know the physics is dominated by electronic correlations. That's where, near here is where all the physics, interesting physics occurs. And yeah, I want to draw attention to this point in the Brouin zone. So this is a plot of energy as a function of momentum in the Moiré Brouin zone. So energy as a function of momentum, where you only keep these leading terms in the a wave vector expansion of interlayer tunneling. And so there's this point, which is the point in the momentum space, which is furthest as far away as you can get from a Dirac point. And you can see that the energies here at 2 degrees are very far away from the flat band energy. Whereas at the Dirac points, these energies are already in this region of momentum space. There's not much dispersion in these bands, even at 2 degrees. And you can see here that in this calculation, even at the magic angle, if I look at the gamma point in momentum space, the states that were, the states that are in these other bands that are further away are very nearly just at the gamma point, only at the gamma point, that they are not very far away in energy. Okay? And so this distinction between regions of momentum space kind of near these near the Dirac points, and which are, let's say, kappa points, I'll call them, and gamma points is something I'm going to make. Okay, here's one of the ways. Okay. Okay, so it turns out that the energy at near gamma, the bands near gamma, are very sensitive to details of the modeling Hamiltonian, and that's one of the things that makes a big challenge in doing predictive modeling, as I'll explain. So this is actually this is a plot of how the energy separation. This is a plot of the energy separation between the flat bands at the magic angle, or near the magic angle, and these what I call remote bands, these higher energy bands. And you can see that this is the region where of Rafi's calculation, and that separation is for very small. So the vertical axis here is the ratio of intra-sublattice tunneling between layers and to inter-sublattice tunneling between layers. And we now know that that this ratio is smaller than 1 because of a combination of corrugation and strain effects that I'm sure have been mentioned already. Basically, most simply, the layers, it turns out, are further apart in the region of the Moiré pattern when you have AA hopping. And so that property has a big effect on both on the separation in energy between the flat bands and the remote bands, and on the actual wave functions of the flat band electrons. So I've written here approximate, but turns out pretty accurate expressions for 12 energies at the gamma point. These 12 energies come from the six Dirac cones that are equally spaced relative to equally far away from gamma. So there are 2 levels for each of these 6 Dirac cones. So there are 12 levels. You can see there's 2 signs here, 2 plus minus signs. So this is actually 4 levels. And it turns out that all of these states are twofold degenerates. So there are 8 of these, actually. So these are all of the energy levels. The ones we're interested in have a small energy, and they're associated with the 2 terms in round brackets having a minus sign between them. A and B here are interlayer tunneling in units of, this is basically the energy at gamma with no tunneling between the layers. And so A is, ratio of tunneling to kinetic energy is the dimensionless parameter that controls the properties of these systems, which is more or less twist angle. And so these dimensionless parameters are close to 1 near the magic angle. And so there's A and B here. And this is simply the dimensional, A is the dimensionless interlayer tunneling intra-sublattice and inter-sublattice. Okay, so the A and B have the same value in the original calculation we did. And you can see that these low energy states where I have a minus sign, so you know the energy states at gamma go to 0, producing a flat band when the first term and the second term are approximately equal. And so the low energy states with the smallest value of the factor in round brackets, you can easily tell without going through the details here that it depends on whether it depends on the ratio of B to A, okay? And so when you have, when the low energy state is doubly degenerate, that means there's a positive energy doubly degenerate state, a negative energy doubly degenerate state, then there's no gap between the flat bands at gamma and the other ones. And that's really what is behind you know, the fact that these bands are practically touching here. There's really double degeneracy for both the positive and negative energy states. And so the experimental corrugation effect, which makes TAA different from TAB, actually turns out to make the low energy state at the magic angle a singly degenerate one. So that's why, in that case, the low energy states are separated. Okay. But we don't know exactly, you know, what this parameter should be. And as I said before, you know, the strain pattern, for example, which is one of the details that's important in these systems, is can be accommodated within the same approach. Appears mainly in the fact that maybe higher coefficients in the Fourier expansion might have slightly different or larger values, and so those details basically control which of these states is lowest in energy, and what the nature turns out of the wave functions of these states is. And when you start to do interacting electron systems, it's not just the energy of the electron that's important, it's the wave function. And so I'll come back to that. Okay. Okay, I have to watch what I'm doing here. Okay, taking too long. And yeah, maybe I'll actually skip this. So I think this is all stuff you know. You know, when you have Dirac cones and interactions, there's a tendency to gap the Dirac cones. And when you gap the Dirac cones, you get bands with, when you gap the Dirac cones, you get bands that have non-zero Chern numbers. And physically, that's manifested through a gift from God that, you know, non-zero Chern number is something easy to measure because it produces, it's actually an observable, the Hall effect, which is an amazing thing. So as I approach the magic angle, you know, the physics is really fairly simple. If the interactions are strong enough, you gap the two Dirac points that are present in the isolated layers, and turns out symmetry preserves them. So the interactions gap them and make bands near Moiré bands, which are near one microscopic so-called valley or another, near one point in momentum space or another. It gaps them and produces bands that have non-zero Chern numbers and therefore should exhibit a quantum anomalous Hall effect. Okay? So that's kind of what's going on here. The bands are getting flatter and flatter. Turns out the flatter, of course, the Dirac cone is, the weaker the interactions that are sufficient to gap them. And whatever environment you're in, as you approach the magic angle and the velocity goes essentially to zero, you will gap those Dirac points. Basically, this phase diagram becomes more complicated as you go to smaller twist angles and stronger interactions. And all of these other things here are got to do with the fact that the remote bands become important eventually. They're not really isolated. Okay?
I'd be happy if you gave us like 30 seconds on each of your slides there.
Yeah.
If you're willing. Yeah.
30 seconds on?
No, I don't want you to cut your lecture short. I'm just speaking personally as the organizer.
You can make any request you like.
Yeah, don't just run through your slides fast. Just let us see everything.
Okay.
Yeah, that's my request.
Okay, you want to see these?
Well,
okay.
So,
yeah.
Now that you did that, I have a question.
Yeah, go ahead.
30 seconds. If you go back to, you used the word universal that I was a bit
Yeah.
But yeah. So in what sense is this universal?
In the sense that up to a scale factor, so when I have two coupled two decoupled graphene sheets, each sheet is described by a Dirac model, right? They have two linearly crossing bands at two different points in momentum space, and these are the valleys I'm going to refer to, right? And we can classify electrons more or less as belonging to one valley or the other. And so these two crossing states, they cross linearly, and the slope of that derivative of energy with respect to momentum is a velocity in quantum mechanics. And that velocity people usually call Dirac velocity, right? And it's that velocity that becomes very small as you approach the magic angle. But the electronic properties of this system depend only on the strength of this term. Okay, because of the various things I've been saying, this sublattice-dependent interlayer tunneling, at least in this approximation, depends only on one number. Okay, and so it's only the ratio of that number to the this Dirac energy scale that controls the properties. Okay, and it's actually the Dirac energy scale, the energy linear in momentum. Quantum mechanics, momentum is related to 1 over length, right, by Heisenberg uncertainty principle. And the relevant length, it turns out, is the Moiré period. So it's, h bar Dirac velocity divided by Moiré period is one length scale. That length scale depends on the twist angle, right? And so if you say that you know the Dirac velocity and you know the strength of the interlayer tunneling, and we know them, I think Palco would agree with me, to at least sort of 10-20%, it's good enough for us, 10% perhaps, then everything depends just on twist angle, okay? So say the twist angle, that's it. So to a good approximation, even this complicated pattern of bands depends only on twist angle.
Thank you.
Yeah. Okay. So yeah. So I'm going to skip this, but I'm happy to talk to anybody.
So I'll schedule you after.
Okay. Yeah. Okay. Yeah. So, the wave functions in the flat bands depend on details that we don't necessarily, that depend a lot on twist angle. Experimentalists don't necessarily have perfect control over twist angle, and they depend on strain patterns and little details that are very sensitive, okay? We're going to have a lecture, I think, this afternoon from Andre Young, is that right?
Yes.
And so I think he'll talk about magic angle twisted bilayer graphene, and so we'll get a good summary of all of the advances people have made in understanding the pattern of behavior. This is the phase diagram, actually not from the original paper by Pablo Herrero Herrero, but a related set of data described in this color plot. Resistivity map by Dmitry Yefetov, and it shows, competing insulating states in red and superconducting states in blue. Okay, and we have these flat Moiré bands. Each of these Moiré bands has a flavor quantum number, spin as usual. There are 2 spin states that are degenerate, and turns out there's states at 2 different valleys, which are 2 different microscopic momenta related by time reversal symmetry, and they're all degenerate. Okay, all of these bands are degenerate, and system at neutrality. That means that the so-called valence band, if I use semiconductor language, the negative energy flat band is filled and the positive energy flat bands are empty, and that's observed to be an insulator pretty consistently now, and that is understood in terms of, most simply stated, in terms of this breaking the Dirac cones. So this broken symmetry here, which is actually breaking the sublattice symmetry of the Dirac cone, of the individual layers to make a gap in the Dirac system because the velocity is small, means that I have 4 bands at this point, all degenerate, with different flavor indices, if you like, and each of those bands has non-zero Chern numbers, but these bands appear in pairs that are related by time reversal, and it turns out that means that they have opposite Chern numbers. Okay, so 2 have Chern number 1, 2 have Chern number -1. And what is pretty consistently seen, now we know that if you make the Coulomb interactions weak enough, these insulating states here, some of these insulating states at partial filling of the valence band, this is experimentally using gates to occupy and empty the valence band, and on the right it's using gates to occupy and empty the valence band, these insulating states are understood in terms of breaking flavor symmetries, just like we do in a magnetic metal where we, let's say, only occupy upspin states. And because we only occupy some of the flavors, the gap between the conduction and valence band can produce an energy gap. And so it seems like that is the nature of the insulating states. And also there are details in these plots that I won't discuss, which suggest that those broken flavor symmetries is like having a 4-valued spin, if you like. So it's a kind of ferromagnetism. And there's indications in this data that the broken symmetries are present in the metallic states as well. Metallic states, I mean going away from the insulating states at all of these points. There are 2 different ways of counting this. This is filling factor -1 in one way of counting. All the valence bands are empty. +1, all the valence bands are filled. But if you count each of the flavors, then this is -4 and this is +4. And in that language, insulating states appear at all, or at least most of the integers, most of the time. When it's metallic, most of the time, if you go to low enough temperature, it becomes a superconductor. So it turns out we do see the quantum anomalous Hall effect in this system, as Andrea Young may discuss. And I'll talk about how that happens a little bit. Okay? So somehow it must involve broken time reversal. So there's lots we don't know, and maybe the mechanism for superconductivity I'm going to talk about in a moment, and maybe we know more about that now. Okay. Okay. So this is a calculation. So I'm going to try and sort of compare what we know about this compared to what we know about copper. Okay. This is actually a theoretical calculation. It's a calculation of energy normalized in some way that's not important as a function of filling using for taking electrons out of the system, starting from neutrality, removing 1 electron per Moiré period 2, 3, 4, right? And so you see, according to these mean field theory calculations, which are generally pretty consistent with experiment, that at most filling factors, the fourfold flavor degeneracy is lifted. And the blue line here is a mean field calculation which doesn't allow flavor symmetries to be broken. The, orange one is, let's say, a ferromagnet where you allow a difference between the occupation of upspins and downspins. In the green curve is you allow, even within each spin, you allow different occupations of the two valleys that are present for each spin. And so this kind of calculation that in this region of the phase diagram, you completely break the flavor degeneracies. Close to 0, maybe you don't break any degeneracies. Close to -2, maybe you only separate the 4 flavors into 2 in one group, 2 in another group, let's say spin up and spin down. So this is, generally speaking, fairly consistent with experiment and can be understood fairly well with at a mean field theory level. So now let me turn to where we get into trouble that I was leading to in the first part of my talk, and this actually touches on points that have been made first by our chairman, and this is actually Fock self-energy, and I'll explain what this is in a moment. We could do the same thing for the Hartree self-energy, which Paco emphasized in his original work on this. Let me look at just talk about this curve. Okay, the energy of a quasi-particle is influenced by electron-electron interactions. And for example, in density functional theory, the cone-sham energies are very different from the non-interacting electron energies. This is actually in the context of a Hartree-Fock mean field theory calculation. And so those shifts in the Hamiltonian due to interaction effects are called self-energies. And so it's an operator that acts in this flavor space. And acts in particular, I should say, in the space of the various bands. It's not necessarily diagonal. And but the main thing I want you to notice here is this is a plot of interaction shift in energy, if you like, as a function of momentum. And the way the momentum space is drawn here, which of course momentum space is finite for a periodic system. The way it's drawn, the gamma points I was talking about before appear right here, and it's equivalent to a point on the other side right here. So you can see there's some triangular region, actually very strange triangular shape region. If I put this little vertex on top of this base over here, it's a triangular shaped region where things are different from the kappa regions of the Brouin zone, which are kind of in the middle the way this is drawn. And the reason that the self-energy effects are very different is because the wave functions are very different, okay? But exactly what they're like depends on details of the Hamiltonian. So this is kind of part of the challenge we face in getting to the same level of understanding that we have for, let's say, simple metals.
Can I ask you a question?
Yeah.
Sorry. So what is the definition of the Fock self-energy?
Yeah, so it is, so, let's say in chemistry, when you do a Hartree-Fock approximation, there's a Fock operator. Here I'm calling it a self-energy.
Okay.
Yeah, okay.
Thank you.
Okay. So this is another plot that makes the same point. What's drawn here are the black dashed lines are energy as a function of momentum in the Moiré-Brouin zone for some particular value of TAA over TAB of the ratio of intra-sublattice to inter-sublattice tunneling. And you can see because this ratio is not 1, there's a reasonable separation here between the flat bands and these remote bands. But nevertheless, the single particle flat bands always have their band extrema, the bottom of the valence band, the top of the conduction band is always at gamma. Okay? And the blue bands are just include these self-energy effects, both Hartree and Fock. And as I said, the biggest effect for what I'm talking about here is the Hartree self-energy, as Paco pointed out some time ago. And this is at a particular interaction strength. And so if I just talk about the Hartree, maybe that's simpler to describe. And this is the self-energy when the flat bands are empty, okay? And what it is if I look at all of the charge density when the flat band is empty, when the flat valence band is filled, that's neutrality. There's a particle hole symmetry property that says the density is practically uniform, okay? When the flat band is empty, then there is a deficiency of charge near AA points, near AA stacking in the Moiré pattern. And so electrons are attracted to those AA regions. But how they respond to this potential depends on their wave function. And the wave functions at gamma near gamma have less weight near these AA regions. So they're actually pulled down less. Or if I shift them so that their energies at the gamma stay the same, that means the energies at gamma go up from this self-energy effect. And so you can see the bands look entirely different, right? This conduction band is driven up even at this hopping parameter so that it is it's now touching the remote bands. There's an avoided crossing here near gamma between between what was originally the flat band and this remote band. And most importantly, it's no longer true that the band extrema, let's say at the bottom of the valence band, here is no longer at gamma. So if we look at things that we normally look at in crystal, like filling a band, and this is actually, I'm not sure if Andrea will discuss this, but this is very closely connected to things you can measure. The simplest thing you can measure is the Hall effect. And so it turns out there's something that you can dig out of Hall effect transport measurements which in the case of an isotropic Fermi surface, you can prove that, if I have a metal with a partial, in other words, a system with a partially filled band, then and it has a closed Fermi surface, then if the occupied states are inside that Fermi surface, the Hall effect is one sign, and the magnitude of the Hall effect measures the area inside that surface. And if the Hall effect is the other sign, it also measures, that would correspond to a isotropic Fermi surface, where inside the Fermi surface you have empty states, okay, hole-like states. And time to stop. So I will stop after this point, and then maybe just flash through things, see if anybody wants to chat about. So what this is showing, when I start to fill a band, or I could say something similar about starting to empty a band, here, this is a circumstance where the bottom of the band was near gamma, which would be the non-interacting electron result. So you get this behavior if interactions are weak enough. You start off with these funny triangular shaped, very anisotropic Fermi surfaces. Turns out that these don't satisfy this rule I told you before that experimentalists generally assume is true, that the density you dig out of the Hall effect really measures the area of the Fermi surface. The shape of the bands depends on uncertainties with both single particle and interaction physics, and these can be measured, and there are some clues I don't have time to discuss from, let's say, Hall effect measurement. But the real powerful measurement we would love to have, which I think is coming, not there yet, is angle resolved photo emission. So you can really measure which states are occupied in momentum space on this energy scale. Okay, now, so this is the flashing through part. Anybody wants to talk to me about these things, they're welcome. Superconductivity, this is an illustration from a paper I wrote with Fengcheng Wu about superconductivity mediated by optical phonons. I think the general, I think that there's a lot of evidence that suggests this is the right mechanism for superconductivity in these systems. I won't have time to talk about this in detail. The second thing is the quantum anomalous Hall effect, which has now been observed in magic angle twisted bilayer graphene. In addition to superconductivity and interesting insulating states, particularly interesting insulating state, a Chern insulator, which has a quantum anomalous Hall effect, has been seen. And I think that the way to understand that, and this has maybe been suggested first by Senthil at MIT, is that it's due to spontaneous valley polarization. It's very natural interpretation. We have these two valleys, they have Chern numbers, and if you break the flavor symmetries and such that you occupy the bands that, more bands that have Chern numbers of one sign than Chern numbers of the other sign, that gives you a Chern insulator. And this is actually, there is a strong interaction reason why electrons would tend to valley polarize, why they want to occupy only one region of momentum space. And it's actually, amusingly, connected to something which is, you can find, a history of physics articles about, which is about an incorrect theory of superconductivity by these two famous scientists, in which they suggested that condensation, as they called it, in momentum space, which is what happens with the quantum anomalous Hall effect, could explain superconductivity. Doesn't explain superconductivity, but it does explain the quantum anomalous Hall effect, which is a broken time reversal state, and it's a broken time reversal state, not with spin like we're normally used to, but with orbital degrees of freedom. and that leads to very unusual magnetic properties. And that is this part of my talk. And the final thing is that transition metal dichalcogenide artificial Moiré superlattices, it's already clear, are extremely interesting. Material qualities not at the same place yet, but there's a lot of things to explore, both in transition metal dichalcogenides, maybe magnetic systems, and presumably in many van der Waals materials we still haven't thought of. So thank you very much.